Hi everyone, this is Erica Podest and welcome back to the Introduction to Synthetic Aperture Radar webinar series. So far we've covered the basics of synthetic aperture radar. That was session 1. Session 2 covered SAR processing and data analysis, and this is the third of the 4-part SAR webinar series. And today we'll be covering Introduction to Polarimetric SAR. Our guest speaker today is Dr. Nayara Pinto. She is the science coordinator for UAV SAR, and she is based at NASA's Jet Propulsion Laboratory. Welcome.
Thank you, Erica. So thank you everyone for participating today. My name is Nayara Pinto. I am going to present today about the Introduction to Polarimetric SAR. And I'd like to acknowledge a few researchers that helped produce this material over the years from NASA and the Alaska Satellite Facility. So what are our learning objectives today? We saw from session 1 and session 2 that radar signals can interact with the Earth's surface. So essentially, the radars illuminate targets on the ground, and then they record the received energy that's also called backscatter. The received signal provides information about properties of targets on the ground or scatterers. And more information is gained by studying different polarization. By illuminating the targets with waves of different polarizations, we learn more about the target's physical properties. So our goal today is to provide a brief introduction to polarimetry and help students familiarize themselves first with the way that the polarimetry information is represented mathematically, second, the data format, and third, provide one example of data processing for land cover mapping. So let's get started. Our outline is we're going to start talking about why polarimetry. I know a lot of our audience is coming from the optical world. A brief introduction on polarization, and then we're going to move to scattering mechanisms. Then talk about data and software. We're going to cover 2 instruments today, one that's spaceborne and one that is airborne, and including analyzing dual pole and quad pole imagery. And last, we will display the results of our classification. So why polarimetry? So here's one image of an area that our group was studying last year. It's Libreville in Gabon. And we can see here several land cover types. We have a forest, we have mud banks, open water, and different types of vegetation. Mangroves that are dense, more tall mangroves. We have dry forests. We have urban areas, the city of Libreville itself, and we have exposed ground. The airport is a very good example of that. So the question here is, how can we use SAR to complement optical data and resolve some land cover types that cannot be mapped with reflectance data alone? So here's the same location imaged by the UAV SAR instrument in Libreville. We flew this area in March of 2016. So as you can see, you can resolve a lot of different land cover types. This is a false color image, meaning that the colors that you see here are capturing different polarizations. So the red channel has HH, the green channel has HV, and the blue channel has VV polarization. So during this presentation, I hope that you will gain some intuition about what these different bands are providing in terms of land cover information. So radars produce microwaves. they are electromagnetic waves. And the direction of the electric field lies in the plane that's perpendicular to the direction of propagation. And that's defining the polarization of the wave. In our case here, we're going to talk about two different types of polarization, vertical and horizontal. So in dual pole instruments, the instrument transmits H or V, meaning horizontal or vertical, and they receive H and V simultaneously. Then if we talk about a quad pole instrument, those are able to transmit H and V and alternating the pulses, and again they receive H and V at the same time. So this is one table summarizing dual and quad pole instrument. The dual pole instrument we will study today is Sentinel, so the data set we have corresponds to this column on the table, transmitting V and receiving VH and VV, or receiving H and V. And the other instrument, UAV SAR, is quad pole, which means we transmit H and we transmit V, and we also receive H and V. So you have all those four bands in a data set. So again, the amount of returned signal for different polarization depends on the physics of how the signal interacts with targets on the ground. So you can see how having polarization diversity helps you resolve different land cover types. So here is one example from the recent literature. These authors were studying land cover types in Canada using the ARSET instrument. So radar polarimetry is defined as the study of using multiple polarimetric returns to infer information about a surface. There are many applications for mapping land cover types with polarimetry, and that includes cryosphere, vegetation studies, and hydrology. And if you look into the literature, you'll find two main types of studies. Some researchers are concerned with building theoretical models. They sometimes are also called forward models that simulate the scattering of the signal over different types of surfaces. So those are more theoretical models. There are also more empirical studies that show with observations what the signal is at different land cover types. So we are looking into different polarization signatures. So what we want to understand is how do you navigate this literature and get the most information for your own studies. And to do that, you have to understand the basic concept of scattering mechanisms. So the features we see in polarimetric images are due to different scattering mechanisms, meaning that the received signal changes as it interacts with targets on the ground. And here are three types of important scattering mechanisms. You have a surface, which is something you might find on exposed ground. You have volume scatter, which is common in vegetation and tree canopies. And you have also double bounce, which is when you have two perpendicular surfaces. And this is common in urban areas, where you have these flat surfaces like buildings. So the first thing we need to understand is how this information can be encoded mathematically, and it's represented in a scattering matrix. In the quad pole scenario, when you have HH, HV, VH, and VV, this information is encoded in a 3x3 coherency matrix, also referred to as a T3 matrix. So this is what it looks like. And during the course of your work, you're not going to have to compute this matrix, but this is the starting point for any analysis. And if you work on polarimetry software, it's going to prompt you, what matrix do you want to store your data? So it's useful to understand that. What would I like for you to take from this? Well, first, there are some complex numbers here. So the star denotes complex conjugation. And this essentially means that this matrix has information about the power as well as the phase of the received signal. The other thing that's relevant is that we are doing some averaging here, which means for each pixel, we are using a moving window to calculate those quantities. So all 9 elements of this matrix are calculated for each pixel in your image, using averaging, using a moving window. So again, as a first step of working with polarimetric images, you're going to be prompted to select the size of this window. And this is how the size is used. It's used in the averaging during the construction of the scattering matrix. And then the next step would be, okay, now that you have all this information, could you reduce this to a limited number of descriptors to understand the scattering mechanisms on the ground? So what I'm going to do is to provide you with one example of how you can do this, and that's called a decomposition. There is many different decompositions that we can do, but this is a commonly used in the literature, so this is why we're doing this one today. The H-alpha decomposition is based on the eigenvalue and eigenvector decomposition of the T3 matrix. So we're starting off with our coherency matrix, and we are applying some matrix algebra there to get to this part. So these lambdas are my eigenvalues, and the U3 are the eigenvectors. The important thing to know here is that by doing this, you get independent scattering mechanisms. The eigenvalues are used to calculate entropy, and that's referred to as H. And the entropy is a function of noise owing to depolarization. So essentially, it's the same entropy that you use in diversity studies in biology and in other studies in thermodynamics. And the idea is how likely are these different states to be found in your pixel. So with a low entropy, entropy closer to 0, you're more likely to be dominated by a single scattering mechanism. And with higher entropy, closer to 1, all scattering mechanisms are equally likely to be found in your pixel. Entropy is a dimensionless unit, and it goes from 0 to 1. And this is one example. This is a site in Costa Rica, and you can see at the top you have a screenshot of Google Earth. And we can see some plantations here, and you can see mangroves here. And these are all green, right? You don't see a lot of difference in reflectance in those areas. But when you move to the entropy results, you can see that the mangroves have higher entropy. There's more noise in the mangroves because of the canopy shape, whereas more regular plantation sites have lower entropy. And then when you move to bare ground, the entropy is even lower, closer to 0.1. So we talked about H. What about alpha? Alpha is also based on the same decomposition. It's another output that you get out of the same decomposition. And this is alpha. It's part of the eigenvector result. And the important thing to know is that alpha is an angle, and it represents the dominant scattering mechanism in your pixel. And this is how it's calculated. It ranges from 0 to 90 degrees. And this is what it represents. So alpha angle closer to 0 means we have a surface. You have surface scattering. As you get closer to 45, you have volume scattering. Volume scattering sometimes is referred to dipole because volumes or elements like canopies, they're usually modeled as dipoles. Dipoles are cylinders. So canopies can sometimes be modeled by several cylinders, randomly oriented. And then at 90 degrees, we are approaching a dihedral scattering, which is double bounce, which is again what you would see in buildings. So then, using the information from alpha and entropy, we can develop an unsupervised classification. The idea is to have different regions that have values of entropy and alpha, and they have distinct scattering mechanisms. So it's a two-parameter system used to classify different types of scattering behavior. We have 9 zones. As you can see here, it starts as zone 1, 2, 3, 4, 5, 6, 7, 8, 9. Although this zone is called an unfeasible zone, so we're not going to see a lot of values in this area. We're going to focus on the 8 values here that are inside the feasible zone. And when you do this classification, the results can be combined with other layers. It doesn't have to be the end point of your research. Actually, it's a very good starting point to understand the physics of what you see on the ground. And this is one example, a recent example of a paper, again using RadarSat imagery. So for entropy, entropy is on the x-axis, and again, we have values ranging between 0 and 1. You have 3 regions. It's very straightforward, low, medium, and high entropy. Then if you move to alpha, you all have 3 regions, surface, dipole, or volume, and you have multiple, which is a dihedral or a double bounce. So let's do some examples to see what this looks like for a real data set. The first thing I want to do is to look into Sentinel data. Although Sentinel is not available at 4 polarizations, you can still do band ratios. You can compare the amount of received signal for VH and VV, for example. And because Sentinel is available almost globally and with a very good temporal sampling, I think that's a good starting point. The first step that I did was to download Sentinel from the Alaska Satellite Facility. I downloaded an image covering Libreville, the area that I showed at the beginning of this presentation. And to recall that the Sentinel is a C-band instrument, so the wavelength is around 5 centimeters. It's a spaceborne instrument. It's operated by ESA, the European Space Agency. We have 2 polarizations in this case. We are using the GRD product, and the resolution is 10 meters. In this case, I'm showing you how to download one product. At the end of the results, I will show you how to combine information from 2 different days. It does help to do temporal filtering in this case. It helps to beat down the noise. So we're going to do 2 dates today, but you can do more than 2 dates. I'm not going to go into details into the Sentinel processing because this was the focus for session 2. I'm just going to summarize here the basic steps. We started with a zip file. We subset the data, and then we calibrate, we multi-look and geocode the results. And the results that I have here are saved as GeoTIFF files because that's my personal preference, but as long as you can bring them into QGIS, we are fine. And at the end of the day, we have 2 files, VV and VH, to bring into QGIS. And I use the SNAP data, the SNAP software to do this analysis, just like you did for session 2. The UAV SAR processing requires more work, but you also get more interesting results because you have 4 polarizations. Since this is new, I'm going to more details with you today. So UAV SAR is the uninhabited aerial synthetic aperture radar. It's an airborne instrument, so it's a radar that's flying on the belly of an airplane. It's an L-band radar, so the wavelength is bigger than Sentinel. It's fully polarimetric, so 4 polarization. And we are using the GRD product, meaning it's geocoded. It's in WGS84 projection. And the resolution is about 6 meters. So if you go on the UAV SAR webpage, you can download this product. And if you go on the data search page and click on the product, this is what you see. You see a list of links, and what we want is the orthorectified product. We don't want the slant range products. Those are in radar coordinates, so it will be very hard for us to overlay the results with other data sets. So we want all 6 GRD files. The KMZ file helps us have a quick look of the data. And we also want a metadata file that's also called the annotation file. The software used to do a polarimetric decomposition of UAV SAR data is called PulsAR Pro. PulsAR Pro was developed by the Institute of Electronics and Telecommunications of Rennes, and they are now in charge of supporting this package. It's available for Windows and Linux, and you can also compile at Macintosh using the Linux source files. That's what I do. And you can use a graphic user interface or a command line interface. And today I'm going to use the command line interface because I work on a Macintosh. But I'm showing here one example that's also posted at the UAV SAR website where you do another type of decomposition using the graphic user interface. So I recommend that you try it as a comparison. And if you're more comfortable with GUI, you see that the steps are the same. So when you go into PulsAR Pro, the GUI interface, your first window, looks like this. For the command line interface, you would open your terminal and go to the soft directory. The soft directory has all the software, has all the routines, and it has all these different directories. So the most relevant for us and the ones that I use more frequently are the data import, which helps us ingest the UAV SAR files, the BMB process that helps us make some quick looks, and the data process single, which gives us all the classification and decomposition routines. So if you just are curious about the routine, it's easy to just type that routine name on the terminal to see its usage. So for example, if I go to the directory soft/dataprocess_single, and you type Wishart H alpha classifier, the Pulsar Pro is going to complain because there is no arguments to this function, but then it's going to give you the usage. So these are the parameters. And there are some parameters that are very common to every function. Your input directory, your output directory, for example, and the offset row and column. This is used to subset your image. We're not going to use it today, but it can be useful. And other input files for this function and optional parameters. So as we discussed before, the first step is to ingest our image and make a coherency matrix. We don't have to do that by hand. Pulsar Pro will do everything for us. So all you have to do is to call this function, UAVSAR_convert_MLC.exe. And what you give to Pulsar Pro is your annotation file, which is here. And you provide the names of all the GRD files. Remember, there were 6, so 1, 2, 3, 4, 5, 6. The output directory, I'm calling it T3, but you can call it whatever you prefer. The output directory format is T3 because there's many different types of scattering matrix, but today I'll focus on T3. The input number of rows and columns is something that you can find in the annotation file. It's just the size of your raster. The offset row and offset columns, as I mentioned before, is 0, no offset today. The final number of rows and columns is the same as before. And I'm taking looks in rows and columns. So Erica talked about taking looks in session 2. We're going to do the same here. So 2 by 2. After this, we're going to have a T3 matrix. After you have the T3 matrix, you can call any decomposition you want. But today, we're going to focus on the H-alpha decomposition. So this is how you would call from the command line. It's the H_A_alpha decomposition. And the input directory is T3, which, as you remember, was my output directory before. And my output directory, I'm calling it decomposition. The format is again T3. And remember we talked about how we take a moving window to calculate the values in the T3 matrix. So this is what we're talking about here. You have a window in rows and a window in columns, and this is what's used to do our calculations. So this is relevant, and I'm using 7 by 7 window here, but you could use a larger number. You could use 9 by 9, 10 by 10, and play with the results. The final number of rows and columns is something that depends on the number of looks. So because I was taking 2 by 2 looks, this number is half of what I had initially. And these are some flags indicating the outputs that I want. The flag 2 and flag 3 and flag 4 will produce the entropy, alpha, and another interesting parameter called lambda. So you can make a flag of 1 for all of them and inspect each one of the files if you prefer. Then once you have your results, what you would call is the classifier. The classifier would take the decomposition results and define the zones. So each pixel is assigned a zone between 1 and 9. So you are providing, again, the input directory, which is the directory where I put all the results for this function. You have an output directory, which you can name whatever you prefer. I'm naming it the classification. Offset is 0, as before. The number of rows and columns hasn't changed, it's the same as before. And these are the types of classifications that can be done. And I decided to do today an H alpha decomposition or classification, sorry. So this is set to 1. And PolSAR Pro has a set of color tables, so I'm giving it a color table. Later, when you get your result, it's going to be a binary file, and you're free to change the colors. As a last step, you need to get your binary file and open it in QGIS. In order to do that, there is one intermediate step. You have to make an NV header. The NV header tells QGIS how big your image is, the number of rows and columns, and where it's located on the map, and the pixel size, as well as the data type. So this is one template NV header. And you don't have to work with the NV software. QGIS will read images with NV headers. And also ArcGIS, starting at 10, they will read NV images. So what you need to change here is the number of samples and lines. And that's going to be found in the config file that the PolSAR Pro produces. It's a small text file, and it's also the numbers that we have here. But if you want to confirm, you can go to the config file that is produced by this routine. And then for the UAV SAR annotation file, you would grab the location of the upper left pixel. This is how QGIS would know where to place your image, right? This is an image in Gabon. This is where my upper left pixel is. And I also need to provide the pixel size. So this is the pixel size for the original UAV SAR image. But because I took 2 looks, I multiplied this by 2. So this is the final size, and this is what I have here. So if you have all of this, we're using data type 4 because it's float. You should be able to import your PolSAR Pro results into QGIS. And by the way, this manual step is necessary even if you use the GUI interface at PolSAR Pro. As far as I understand, no NV header is produced. So there is an extra step that's needed to be able to visualize your results outside of PolSAR Pro. So let's bring it into a GIS environment now and get some intuition for the results. First, I want to show you what we can see with Sentinel data. In this case, we're not doing any decompositions. It is possible to do decompositions with dual pole data, but it's not, the results are not as useful, and it's not as common to see those on the literature. However, what Sentinel can give you is a very dense temporal sampling. So what I did here was I took 2 dates, and for the VH channels, I took the mean between 2 dates. And this is what I have here, March 20th and March 8th. And I put that on the green channel. Then for VV, I have 1 date, March 20th, on the red channel, and I have another date on the blue channel. So the question is, can you visualize different scattering mechanisms in this image, which is a C-band image, by the way? So if you start here and you look at open water, calm water, you can see it's very dark. And looking at a few pixels in this area, you will get these values. So those are very low values, indicating this is very dark surface. What we have here is specular reflection. Very little of the signal that is transmitted is received back by the sensor. So that's why these areas are very dark. So the next area that's interesting is the airport. The airport, if you remember, is right here. And the airport is dark, but it's not as dark as calm water. You can see the values are slightly larger, more positive. It's not easy to see it on the image, but you can see it with the numbers. And I expect that surface scattering is influencing these results. So this is surface scattering on bare ground. Next, if you look at the city of Libreville, which is here, if you inspected a few pixels in this area, you would see there's a lot of buildings and you have a lot of double bounce. But this means that the single pole images would be very bright. So you have a more positive value here for VV in both days, and not so positive for VH. So this is something that you observe at the single pole result. You don't see that with a VH or with HV. Now, the last area that's interesting is the forest, which is here, and the tall mangroves, which are these areas here close to the river channels. So these areas have higher VH contribution relative to VV. So what this telling me is that we have more volume contribution. So volume is what gives us a bigger contribution of VH, because when the signal interacts with the canopies, there is depolarization. That means that the incident wave has one polarization and it changes before it's recorded by the radar. So let's look at the decomposition results for UAV SAR now. So first we can look at alpha results, and remember alpha is an angle, and values can range between 0 and 90. We don't have the full range here. In order to get an alpha closer to 90, you have to have an ideal scatter, something like a metal plate. So the values get up to 55 in this scene. And what you see is the open water has low values, as well as the runway. They're not perfect surfaces, but they're closer to being a surface. Then if you look into the forest has a value that's closer to 45, as you would expect, because there's a big contribution of volume scattering. And the same is true for tall mangroves, which are here. And lastly, if you look into buildings, they have the largest value of alpha, which is around 55. So these are the very bright areas that you see here, the city of Libreville. Then this is a map of entropy. You can see how the results are different from what you see with alpha. So we're getting complementary information here. With entropy, you can see that calm water has very low entropy values. So entropy can go again from 0 to 1. And then the runaway also has somewhat higher entropy values, as well as buildings. And the highest entropy you see is forest and tall mangroves. In this case, you have more different scatterers. You have branches, leaves, trunks. This indicates that you have more diversity of scatterers in the vegetated areas as compared to the city and compared to the runway, to the airport. Lastly, there is one measurement that is the total power, or lambda, which is not as commonly talked about in the literature, but I thought was interesting in this case because it's very bright in the urban areas. So I thought it would be worth showing this to you today. So you can see the lambda value for buildings is extremely high, much higher than it is for any of the other classes. So if you do a classification, this is what you would see at the end. And I brought my imaging to QGIS, and I changed the colors to look nicer, and this is what you see. So if you start with low entropy, zone 9 is yellow, and this is my water here. Water is low entropy. And then if you look into the forest, forest is class 5. Class 5 is higher entropy, as you can see here. And class 5 is also in this area that corresponds to volume scattering, as you would expect for forest. So looking at other areas here, we have the blue areas which correspond to the city. That's zone 4. And if you go back to our curve here, zone 4 is dihedral scattering or double bounce. And it has medium entropy, just like we saw before doing manual inspection of our image. And what else is interesting here? These pink areas are more disturbed areas that have bare ground, so disturbed sites near forested areas, as well as mud banks that are bare ground. So this is zone 6, which if we go back into our curve here, they have a lower entropy. Or I'm sorry, they have medium entropy, and they have a lower alpha angle, which indicates surface scattering. So there are different classifications that you can do with these decompositions, but the point here is that they are unsupervised classifications, and they describe the physics of what's on the ground with a few parameters. So they're a very useful starting point for your land cover classification. And if you want to go further into this, I wanted to suggest some additional resources. There are tutorials for PulSAR Pro, which you can find at the ESA website. Natural Resources Canada has a good tutorial on polarimetry, and the link is here. And the European Space Agency has additional training courses, including videos of polarimetry tutorials. With that, I wanted to thank you for participating again, and I'm ready to take your questions. Thank you.